In February 2017, record rainfall pushed California's Oroville Dam to the brink, forcing use of its main spillway for the first time in decades. The concrete failed almost immediately, opening a massive crater as raging water ripped apart 20-ton slabs. With water surging toward an emergency spillway never meant for such force, catastrophe loomed. Engineers had one choice: rebuild a collapsing dam in real time, racing 24/7 against billions of gallons of water. The first challenge was removing the shattered concrete without destabilizing the mountain. The spillway was a 45-degree slope of chaos, thousands of tons of broken concrete slabs, exposed rebar, and undermined bedrock. With water still flowing through adjacent gates, crews couldn't afford to wait. Every movement had to be calculated to avoid triggering a larger collapse. To tackle the debris, crews deployed hydraulic breakers, massive jackhammers mounted on excavators to shatter the damaged sections. Each impact sent concrete shrapnel flying at lethal speeds, creating a dangerous environment. The solution was a constant water spray, which formed a wet curtain that trapped dust and debris while simultaneously cooling the breaker tips to prevent overheating. In areas where rebar made demolition impossible, engineers had to get creative. They drilled hundreds of precision holes and placed low-charge explosives in a carefully calculated grid pattern. The risk was immense. A single miscalculation could fracture the underlying bedrock and compromise the entire mountain slope. When the explosives detonated simultaneously, the concrete fractured along clean lines. This revealed the true extent of the damage. A massive crater, 300 feet long and 50 feet deep, had been carved into the mountain itself. The scene was both terrifying and awe-inspiring, showing the scale of the challenge the crews had successfully managed. The logistical nightmare became immediately apparent. The 45-degree slope meant heavy machinery had to operate at extreme angles, with excavators requiring special counterweights to avoid tipping backward. Every movement was precarious, and one misstep could have disastrous consequences. Crews worked in harnesses tethered to anchors drilled into solid rock, as a single slip could result in a 500-foot fall into the raging waters below. Safety measures were constant, but the pace couldn't slow. The project demanded precision and speed simultaneously. Temporary access roads had to be carved into the adjacent hillside to allow trucks to reach the site. These vehicles made an astonishing 3,000 trips daily to remove debris, highlighting the scale of the operation. The challenge wasn't just moving the concrete, it was figuring out where to put 400,000 tons of it. The solution was an on-site recycling operation so massive it became a city within a city. Crushing plants reduced the concrete to aggregate, which would later be reused in the new spillway. This created a perfect closed loop, saving both time and millions of dollars in material costs, and turning a logistical nightmare into an innovative engineering solution. With the debris cleared, the real engineering began. The new foundation couldn't be ordinary concrete. It needed the strength of bedrock itself. The solution was roller compacted concrete, or RCC, a dry mix of cement, sand, and gravel that's placed like asphalt but hardens like stone. Trucks delivered 21 cubic yards every 5 minutes to the steep slope, keeping the supply constant for the demanding project. Bulldozers then spread the concrete in precise 8-inch layers, preparing it for the next step, compaction. Massive 35-ton vibrating rollers followed, making 10 passes per layer to achieve near-nuclear density. Every pass was critical, ensuring the foundation could withstand the immense forces it would eventually support. This process continued around the clock for weeks, gradually building a foundation that reached 100 feet thick in some areas. The work wasn't just about pouring concrete, it required careful balance and timing. Moisture levels were critical. Too dry, and the layers wouldn't bond properly. Too wet, and the concrete could slide down the steep slope. To maintain perfect hydration, crews sprayed a fine mist of water constantly, while lasers monitored every millimeter of elevation. Precision was everything, and the combination of RCC, heavy rollers, and careful moisture control effectively created artificial bedrock on a 45-degree mountainside. What emerged was not just concrete, it was a feat of engineering, as strong and precise as nature itself. The precision required was staggering. The entire spillway had to maintain a gradient of exactly 0.8%, a drop of less than 1 foot per 100 feet to ensure water would flow smoothly without creating destructive turbulence. Every measurement mattered, and even the slightest deviation could compromise a system's integrity. Laser-guided graders worked behind the compactors, shaving high spots and filling low areas with accuracy down to 1/16th of an inch. The machinery moved methodically, layer by layer, as crews coordinated to maintain an almost surgical level of precision across the vast concrete surface. Meanwhile, engineers faced another hidden enemy: thermal cracking. The massive RCC pour generated tremendous heat as it cured, and if left unchecked, it could cause cracks that would weaken the structure. To manage this, they embedded 300 temperature sensors throughout the foundation, ready to track any rise in heat before it became a problem. Cooling pipes were installed to circulate water automatically if any section exceeded 150 degrees Fahrenheit. The foundation wasn't just strong, it was intelligently strong, equipped with a nervous system of sensors that would monitor its health for decades to come, ensuring both durability and safety. The RCC foundation was just the base. The surface needed to withstand water moving at 150 miles per hour. Enter green epoxy-coated rebar, corrosion-resistant steel bars pre-welded into 20-foot square panels. Cranes lowered these massive grids into position, where workers tied them into a continuous steel skeleton. Innovation extended to the concrete pour itself. To prevent cracking in California's heat, the mix was cooled with liquid nitrogen at the plant, arriving at exactly 55 degrees Fahrenheit. Pump trucks then moved up the steep ramp, placing concrete in continuous 12-hour pours to avoid weak joints. Internal vibrators worked every square inch of the structure to eliminate air pockets, ensuring the concrete settled perfectly. Meanwhile, automated rolling machines on rail systems achieved the surface flat to 1/8-inch tolerance, maintaining precision throughout the massive construction. The result was a 3-foot-thick concrete armor far stronger than the original. Its durability and precision allowed it to withstand forces previously unimaginable, increasing its strength by an impressive 400% and setting a new benchmark in reinforced construction. The pouring operation became a ballet of precision and timing. With only 6 hours before the concrete began to set, crews developed a leapfrog system where one team prepared rebar while another poured, then swapped positions. Every movement had to be synchronized to ensure the flow of work remained uninterrupted and the concrete maintained its integrity. The liquid nitrogen cooling system was itself an engineering marvel. Each truckload required 2 tons of liquid nitrogen injected at the batch plant, dropping the temperature by 40 degrees in just minutes. This rapid cooling allowed the massive concrete sections to maintain strength while preventing cracks that could have been catastrophic. But the real genius lay in the joints. Instead of traditional construction joints, engineers designed shear keys, interlocking teeth between sections that would transfer tremendous hydraulic forces without failure. These joints would allow the concrete to withstand extreme pressure while remaining perfectly aligned. Each key was precisely formed with custom steel molds, creating what engineers called concrete puzzle pieces. When fitted together, the sections would lock under pressure rather than pull apart, turning what could have been a fragile connection into a robust, interdependent system. The result was a seamless, almost organic structure, combining both innovation and brute engineering power. But the main spillway was only half the problem. The emergency spillway, the hillside that nearly failed, needed its own transformation. Engineers undertook the massive task of covering 25 football fields of hillside with roller compacted concrete, RCC, effectively creating a colossal concrete splash pad. This was a carefully coordinated effort that required precise planning and execution to ensure stability. The scale of the operation was immense. To place 500,000 cubic yards of material, the construction ran as a continuous operation, with trucks forming a 24-hour convoy along the access roads. The sheer logistics of moving and placing such a volume of concrete were unprecedented, requiring constant monitoring and adjustments to maintain the flow of work without interruptions. At the spillway's base, engineers constructed massive teeth blocks, concrete structures designed to dissipate the energy of falling water. Each block, roughly the size of a school bus, had to endure impacts equivalent to 100 cars crashing every second. These blocks were critical to preventing erosion and ensuring that the force of the water could be safely managed as it flowed through the spillway. Finally, the entire system was interlaced with 55,000 feet of drainage pipes, enough to stack 10 miles high. These pipes were essential for relieving the water pressure that had contributed to the original failure. Together, the RCC hillside, the teeth blocks, and the drainage network created a robust emergency spillway capable of handling extreme water flow without risking collapse. The teeth blocks represented perhaps the most brilliant engineering of the entire project. Arranged in a staggered checkerboard pattern, they weren't just passive obstacles. Their shapes, some wedges, some pyramids, some complex geometries, were designed through computational fluid dynamics simulations that modeled exactly how water at different volumes would behave. Each block contained ultra-high-performance concrete with steel fibers mixed throughout, making it 5 times stronger than conventional concrete. Beneath them, engineers installed a 3-layer drainage system, gravel beds, perforated pipes, and geotextile filters that would allow any seepage to escape without building up pressure. The emergency spillway was no longer a last-ditch hillside. It was a sophisticated energy dissipation machine that could safely handle flows the original designers never imagined. This combination of advanced materials, meticulous design, and innovative drainage transformed the spillway into a system capable of enduring extreme conditions while maintaining safety and efficiency. The rebuilt Oroville wasn't just stronger. It was smarter. Engineers embedded 1,200 sensors throughout the structure, strain gauges to measure concrete stress, piezometers to monitor water pressure in the foundation, inclinometers to detect the slightest movement, and accelerometers to measure vibration. This data feeds into a neural network that learns normal patterns and alerts engineers to anomalies in real time. The control room now features predictive modeling software that can simulate exactly how the spillway will perform under any conceivable rainfall scenario. But the most revolutionary addition was the autonomous inspection system, drones that fly prescribed routes daily, using LiDAR and thermal imaging to detect cracks or weaknesses long before human inspectors could see them. The dam now has what engineers call proactive defense, the ability to anticipate problems rather than just react to them. Seismic sensors throughout the region feed data into the control system, giving engineers a precise view of how earthquakes impact the structure. This continuous stream of information allows them to monitor stress points and detect even subtle shifts, providing early warnings before small problems become critical. Weather satellites complement this system by tracking storms in real time, while snowpack monitors in the Sierra Nevada estimate meltwater volumes months ahead. Together, these tools help predict inflows that could challenge the dam, enabling proactive management of water levels and reservoir safety. The system also includes underwater ROVs that inspect the reservoir floor for changes in sedimentation. All this diverse data converges into a 3D digital twin of the dam, a virtual replica that engineers can test under countless simulated conditions. This approach allows them to explore potential weaknesses without putting the actual structure at risk. Engineers have run thousands of scenarios on the digital twin, from 1,000-year storms to magnitude 8 earthquakes and multiple simultaneous system failures. The outcome is a dam designed not just to survive known threats, but to remain resilient in the face of unpredictable extreme events. On April 2, 2018, after 200 days of nonstop work by 600 crew members, engineers opened the spillway baits for the first test. Water began to flow gradually, starting as a trickle and steadily increasing to 100,000 cubic feet per second, enough to fill an Olympic pool every 2 seconds. Embedded throughout the concrete, 250 sensors reported every vibration, pressure change, and millimeter of movement. Engineers monitored the readings closely, ensuring that the massive flow wouldn't compromise the structure. For hours, water thundered down the chute, crashing into the teeth blocks and creating a mist cloud visible for miles. The spectacle was both awe-inspiring and tense, as the team waited for the data to confirm the integrity of the repairs. The results came back flawless. Zero movement, zero distress, zero anomalies. The $1.1 billion repair, completed in half the predicted time, had succeeded. Oroville Dam was no longer a liability. Its new spillway had become the most heavily instrumented and reinforced in the world. But the true legacy of Oroville extends far beyond California. The lessons learned from the dam's near disaster and its subsequent repair have influenced engineers and policymakers around the world. What was once a local infrastructure project has become a global case study in resilience, demonstrating that even the most complex systems can be rebuilt stronger and smarter when innovation, planning, and rigorous monitoring are combined. Oroville's story shows that failures are not just setbacks, they are opportunities to rethink the way we design, manage, and protect critical structures. The RCC techniques developed at Oroville have transformed dam repair practices worldwide. Roller-compacted concrete combined with advanced reinforcement strategies allows engineers to rebuild massive structures more quickly and reliably than ever before. These methods have not only reduced construction times and costs, but also increased the long-term durability of repaired dams. Today, engineers in Asia, Europe, and the Americas routinely employ these techniques, proving that what started as a solution to a California emergency has set a new global standard. The predictive sensor networks installed at Oroville have also become a model for modern infrastructure monitoring. Hundreds of sensors embedded throughout the dam continuously track stress, vibration, pressure, and environmental conditions, providing real-time data to engineers. This proactive monitoring system allows for the early detection of potential issues before they escalate into crises. From water management authorities to urban planners, infrastructure teams around the world now look to Oroville's sensor network as an example of how technology can turn reactive maintenance into predictive, data-driven decision-making. Emergency response protocols developed during the Oroville repair have likewise been adopted globally. The rapid mobilization of thousands of workers and millions of tons of material within a matter of days demonstrated an unprecedented level of operational coordination. These protocols provide a blueprint for responding to large-scale infrastructure emergencies, showing how preparation, logistics, and precise execution can prevent localized failures from turning into widespread disasters. The lessons learned here are now being applied to bridges, dams, and other critical structures in regions prone to natural hazards, saving both lives and resources. Perhaps most importantly, Oroville changed the way engineers approach redundancy and risk management. The new philosophy moves beyond the idea of simply building something strong enough. Instead, it emphasizes multiple independent layers of protection, where every system has backups and those backups have backups of their own. This mindset transforms infrastructure from a static object into a dynamic, resilient system capable of withstanding unforeseen threats. The dam that nearly failed did not merely return to its former state. It became a prototype for 21st century resilience, demonstrating that with foresight, innovation, and meticulous planning, humanity can build back not just to previous standards, but to heights previously unimaginable. The Oroville crisis revealed a terrifying truth. America's critical infrastructure was aging, and failure could come without warning. But the response proved something greater. When engineering, urgency, and human determination align, we can rebuild our foundations even as the water still flows. The spillway that collapsed became a laboratory for the future, where every sensor reading, every simulation, every innovation makes our world a little safer from the next unprecedented event. If this story of rebuilding against impossible deadlines and rising waters changed how you see the invisible structures protecting our civilization, subscribe to the Leviathan Project. What other hidden engineering crises should we explore? The bridges rebuilt while traffic flows? The tunnels repaired under living cities? Let us know in the comments. This is the Leviathan Project. We'll see you at the next structural frontier.